tell you, gentlemen, science has agreed that unless something is done and done quickly, man, as the dominant species of life on Earth, will be extinct within a year.
Mutated ants from the New Mexican desert! A kraken-like octopus with just 6 legs. These are some of the monsters born from the hysteria surrounding nuclear technology. Nuclear, or science, is bound to stir controversy and strike fear in the heart of the uninformed, whether in weaponry or energy generation. This video is intended to combat the epidemic of nuclear phobia through hard science.
In this video, we hope to clarify the technologies used in nuclear power plants, so it is clear how they can help solve energy shortages around the world, and how the challenges they present can be overcome. To do so, we begin with 2 questions. What makes nuclear power plants different than other power plants, and how do nuclear power plants generate electricity? Then, with the help of Nobel Prize-winning physicist Burton Richter, we'll address some of the public's concerns with nuclear power. Nuclear power plants distinguish themselves from more old-fashioned plants in the source from which they draw their energy. Rather than burning fossil fuels, which releases greenhouse gases into the atmosphere, nuclear power plants get their energy from nuclear fission, or splitting an atom into 2 pieces. To understand how fission works, we'll examine uranium, the most commonly used fuel in nuclear power plants today. Uranium is actually a common element on Earth, but we usually don't find it in a form that is useful for nuclear power. 99% of the uranium found in natural conditions is uranium-238. Uranium also has other isotopes, or variations of the same atom with a different number of neutrons. Around 0.7% is uranium-235, and even less is uranium-234. Of these isotopes, uranium-235 is the most important for nuclear reactors, because it can be forced to undergo fission rapidly when it is bombarded with neutrons. Because of this property, uranium-235 is known as fissionable. To build a successful nuclear reactor, uranium has to be enriched to 4 to 5% of uranium-235. Because they have different masses, the different isotopes of uranium can be separated in a centrifuge. Once uranium-235 is enriched, how does one force fission to happen? If a neutron that is unattached to any atom, called a free neutron, hits a nucleus of uranium-235, the neutron will be captured by the nucleus. But this new nucleus is too unstable to survive, so it splits into 2 smaller atoms. In addition, this split releases 2 to 3 free neutrons, which can then go on to split other atoms. Proper functioning of a nuclear reactor requires a controlled chain reaction. When neutrons are released from uranium-235 fission, they split other uranium-235 nuclei, which then releases more neutrons to split more nuclei, and so on. The terms used to describe how fast this process will go are called critical mass, subcritical mass, and supercritical mass. Critical means that on average, 1 neutron released from each fission incident will split another nucleus. A sample of uranium at critical mass conditions will remain at a constant temperature. Subcritical means that less than 1 neutron per fission splits another nucleus, and this will lead to the fission reaction dying out. You can see subcritical conditions on the diagram on the left. Supercritical means that more than 1 neutron per split nucleus will go on to split another nucleus. So in this case, the reactor heats up. This situation is shown on the diagram to the right. In a reactor, you want slightly supercritical conditions to heat the water, but not too much. If the reactor overheats, this could be very dangerous. Now we're ready to see how nuclear power plants produce power. First, enriched uranium is formed into rods, which are then grouped into bundles. These bundles are then put into water inside a pressurized vessel. As stated before, the rods are slightly supercritical, so they heat up. How much the rods are allowed to heat up is controlled by using control rods, made of materials that can absorb neutrons. A machine can lower or raise these control rods into the uranium bundle. The lower they are, the more neutrons they absorb, and the less heat the uranium releases. The mechanism of electricity generation is actually quite simple. The uranium bundle, since it is supercritical, releases a large amount of heat. This heat can be used to boil the coolant water, turning it into steam. This steam spins a turbine, which provides the mechanical energy to power a generator, which produces electricity. While this mechanism is simple, it is also highly effective. The power density of a nuclear power plant, or watts produced per square meter, dwarfs the power density of other forms of energy, such as coal, natural gas, oil, photovoltaic, or wind. So if nuclear power generation eventually comes down to simply using steam to drive a generator, why is it so controversial? One of the biggest concerns is that it produces nuclear waste. There are three kinds of nuclear waste. The first is called high-level waste, and in the context of nuclear power plants, it comes from used fuel from the nuclear reactor, as well as any materials from the nuclear power plant that have been reprocessed. When used fuel is taken out of a reactor, it is still highly radioactive. So what do you do with it? The best option currently available is to leave the waste in a geological shelter that is structurally stable and can be prevented from leaking. This strategy is favored because geological disposal sites are relatively easy to monitor, and the waste could be reclaimed later if needed. An even better solution would be to convert this waste into less dangerous materials by bombarding it with subatomic particles, but the technical difficulties associated with doing this are still being worked out. When uranium is mined, the uranium ore actually is only 1% uranium. So when this ore is refined to extract the uranium, there is a large quantity of extra product left over. But this material, called milltailings, is still radioactive, although it is less so than other forms of waste. Still, it is not safe to leave milltailings out in the open, so one way to deal with this is to bury it in clay pits that aren't close to any large cities. Then, there is low-level waste, which is actually a none of the above or miscellaneous category. If it doesn't fit into one of the other categories of nuclear waste, it will probably be called low-level waste. The best options found so far for storing low-level nuclear waste are to leave it in landfills above ground, or to store it at the sites of the nuclear plants themselves. It's clear that nuclear waste is a major challenge. Even the most benign forms of nuclear waste must be stored for hundreds of years before they are safe, and the most dangerous ones must be stored for hundreds of thousands of years. But many experts believe these obstacles can be overcome. Among these experts is Professor Burton Richter, Nobel laureate and former director of the Stanford Linear Accelerator Center. Here's Dr. Richter giving his take on the nuclear waste issue.
Hundreds of years is no problem. I think hundreds of thousands of years is more of a problem. You put them underground, you seal them up, and people aren't going to get at them unless they do some large-scale excavations. You're not going to have a corps of terrorists with picks and shovels getting at this stuff at any time. So I really don't think that's an issue. The real issue is the much longer term security. If you don't treat the waste, if you go through what's called once through, you have to isolate it for hundreds of thousands of years. There are things that are being talked about, not yet commercialized fully, that take the long-lived components, the actinides, plutonium, americium, neptunium, curium, and burn them up by recycling them, taking them out of the spent fuel, recycling them in reactors and fissioning them so they go away. You do that, and then you're left with the fission fragments. They're two long-lived ones that have to be treated specially, but in the main, it's sort of 500 to 1,000 years. Now, I always say when I give talks on this, that the pharaohs could build pyramids that last 6,000 years. We ought to be able to do something that lasts 1,000 years. That's easy. The one that lasts a few 100,000 years, that's not so easy, but other countries have done it. The problems in the United States are not technical or political.